Okay. All right. So let's get started. So welcome everyone for our last seminar of our OSU AIoT seminar series this semester. Today we are very honored to have Dr. Lily Chu to give us a talk today. Dr. Chu is a well-established and well-known researcher in the area of wireless networking and systems. She is currently a system managing director of Microsoft Research Asia, and is mainly responsible for, overseeing the research, particularly at Microsoft Research Asia in Shanghai. Before joining Microsoft, Dr. Chu was a full professor of computer science at the University of Texas, Austin. She, as I mentioned before, a world-leading expert in the area of internet and mobile wireless networking, and also a leading expert in sensing technologies, particularly contactless sensing based on wireless signals and acoustics. A little bit more background: Dr. Chu obtained her master and PhD degrees from Cornell University in computer science. Before joining UT Austin, she was a researcher in a system networking group at Microsoft Research Redmond. Dr. Chu is a ACM fellow, a IEEE fellow, and serves as the ACM SIG Mobile, the chairperson of the SIG Mobile, which basically a research community in mobile computing. Dr. Chu has many awards received due to her research. She was the recipient of NS Career Award, Google Faculty Research Award, and is the recipient of the Best Paper Awards at ACM Mobisys and IEEE ICMP. And her talk title today is Acoustic-Based Active and Passive Sensing and Their Applications. Without further ado, let's welcome Dr. Chu.
Thank you, Professor Zhang, for your kind introduction and kind invitation. And thank everyone for joining my talk. Yeah, it is my great honor and pleasure to share some of our research on wireless sensing and applications.
So Dr. Chu, you wanted to share the screen.
Oh, yeah, sorry, God.
No worries.
Can you see my screen?
Yes, I can.
Okay, awesome.
And you wanted to turn that into the presenter mode? Oh, yeah, great. Awesome.
Wireless sensing has many applications, such as social distancing, healthcare, smart driving, IoT, VR, AR, and many more. One of the common approach for sensing is using camera. Indeed, a camera sends lots of rich information. But on the other hand, the vision-based approach has a few major limitations. First of all, the moment you turn on camera, it introduces privacy issues. Moreover, it has limited range and field of view. It requires line of sight, and it is relatively power hungry, and also cannot sense certain chemical or physical properties. RF-based sensing is also becoming very popular, such as Wi-Fi sensing, millimeter wave sensing, and they have large range for Wi-Fi, but limited accuracy unless we use a huge bandwidth. Millimeter wave has the potential for higher accuracy, but the availability of millimeter wave devices is still quite limited. So in this work, we mainly consider using acoustic signal because it is easy to find devices with speaker and microphone. They are on our smartphone, smartwatch, smart TV, smart speaker, and many other IoT devices. And we just let the speaker microphone use these inaudible band at around 18 to 24 kilohertz. So the major benefit of acoustic signal is it's widely available. We don't need any extra hardware, and its acoustic signal propagates relatively slower, so it has potential to achieve higher accuracy. Moreover, its a low sampling rate make it possible to do efficient software processing and energy efficiency. In this talk, I will briefly introduce some of our work on device-based active sensing and device-free active sensing. By active sensing, I refers to we actively generate a transmission signal and receive the reflected signal or direct signal from the transmitter. In comparison, we also explore passive sensing, where we sense the natural sound from human speech or other environment sounds. In addition, we also explore a few applications on top of acoustic-based tracking. In our first version, we consider acoustic-based device tracking. We let the speaker emit an audio signal in inaudible frequency, and we track the device movement using Doppler shift. As we learned from our high school physics, due to movement, we will experience a change of frequency, and the amount of frequency shift is direct proportional to the movement speed. Therefore, we can do frequency analysis and find the peak frequency, and then use the shift of the peak frequency to calculate the velocity. And to further derive the distance, we can integrate the velocity over time. And the figure at the bottom right shows a comparison between Doppler-based distance estimation versus ground truth. As we can see, these two curves match very closely together. So in this first version, we are able to achieve centimeter accuracy, which is already much better than accelerometer-based approach. Of course, we want to do even better. And our second version, built on top of the Doppler-based approach, we further improve the accuracy and robustness. In addition to estimate the velocity, we also directly estimate the absolute distance. One of the major challenges in estimating the absolute distance is to overcome the synchronization problem. As we notice, the speaker and the microphone may not belong to the same device. In that case, they are running at different clocks, and there's a synchronization error between the transmitter and the receiver. So we developed a novel approach that uses reference position so that we can remove the need of synchronization. We further leverage IMU whenever available to further enhance the accuracy. And this is the comparison. The top figure shows our first version based on Doppler shift-based approach, and the bottom one combined the Doppler-based approach with the IMU and the absolute distance estimation based on FMCW. As we can see, the second version has a much better performance. The red are the trace trajectory, and the blue are the trajectory used by the user. As we can see, these two match pretty well. They achieve a sub-centimeter level error. We implement a demo based on our latest version. And in this demo, we let the internal speaker of the laptop emit inaudible sound and let the phone running our app receive and process the received sound from the laptop to real-time localize the phone's position relative to the laptop position, and then feedback the user's position to the laptop to update the game state. As you can see, the processing is very fast. We can update the position in 5 milliseconds. We also implement a 3D version. Here, these 4 speakers are commodity speaker, $10 from Amazon. They emit inaudible sound, and then the user running our app receive and process the sound to localize its position in real time. We also implement a VR version of the game, and it's based on similar concept. Furthermore, we can also run that on the smartwatch. As you can see, we have 2 watches, and our app running on the watch real-time track its position based on the sound emitted by the speaker, the rectangle speaker here. And our tracking is lightweight enough so that it can run efficiently in real time on the smartwatch. And it also can tolerate a certain occlusion. Next, let's take a look at device-free sensing. Device-free sensing is attractive because the user may simply want to move their hand to control TVs, IoT devices around them. In this case, both transmitter and receiver are static, and the target doesn't have any device, so we only rely on the reflected signal. This reminds us of IF radar, but IF radar is bulky and expensive. Moreover, it spans ultra-wideband and requires special hardware. In comparison, our goal is to enable tracking of the hand or the finger using mobile device such as phone or smartwatch. So we again leverage the speaker and microphone on these mobile devices. And the face-based tracking is promising for acoustic signal, because in inaudible frequencies such as 18 kilohertz, the wavelength is relatively small. It's only 1.9 centimeter. A movement of 1 millimeter will result into 0.21 pi phase change, which is very large enough to be measured. Therefore, this enables us to do fine-grained tracking at a millimeter level. However, simply using the phase of the received signal is not enough because of the following reasons. First of all, refraction usually have much lower SNR. Even in free space, refracted signal decay at the inverse proportional to the distance to the force power. Moreover, not only we receive refraction from our targets such as hand, but also we receive refraction from nearby furniture, walls. So we need a way to decompose the signal so that we can focus on only the refraction coming from our target. So our idea is to use channel impulse response. Basically, channel impulse response is a vector that contains the phase and amplitude of the channel at different distance. So for example, here we have 3 objects, each at different distance. And if we know our target rough target location, then we can zoom in to the phase related to the channel tab around that target and use the phase around that target tab to track the hand's movement. And we come up with an effective heuristic to automatically select the tab that is near the target. And this is a comparison result. We show a reference trajectory on the screen and ask the user to trace the trajectory using our acoustic tracking, which is the red trajectory. As we can see, these two match very closely, which indicates high accuracy and ease of use. We also implement that on the mobile phone app. In this case, we let the phone's internal speaker emit inaudible sound, and the microphone on the phone will receive the reflected signal coming from the hand and real-time track the hand's movement and update the game state. As you can see, this tracking is very fast and can be done in real time seamlessly in the game. And previous demo shows the case that we can enable device-free tracking when the hand is close to the phone within 1 meter. But can we enable room-scale device-free tracking? Why do we need that? Well, we see there's a significant increase of popularity of smart speakers. Many US and households around the world own smart speakers. Some even own multiple smart speakers. Currently, smart speakers use voice-based interaction, but this face challenge in quiet environments, noisy environment, or require complicated operations such as manual selection. We developed a gesture-based interaction. We think this is complementary to voice-based tracking. So our goal is that by using a gesture, for example, waving a hand, you can turn off the light or change a TV channel. Acoustic-based tracking is very appealing in smart speaker because smart speaker already has the speaker and microphone. Moreover, as we showed earlier, acoustic-based tracking can achieve high accuracy, low cost, and privacy preserving. But the main problem is we rely on refracted signal, and the acoustic signal decay very fast over distance, especially in the device-free setting. Moreover, existing approach does not explicitly leverage the smart speaker setup. So we developed a new approach that leverages the microphone array on the smart speaker. At a high level, we send a FMCW chirp signal, and at the receiver, we mix the received signal with the transmission signal, and we can show the mixed signal is a 2D sinusoid whose two frequencies correspond to angle of arrival and distance. We further enhance the 2D musical algorithm by developing several signal processing methods, such as time domain beamforming, optimizing microphone placement using middle chirps, and remove negative frequencies, as well as estimating the initial position of the target. In the ideal environment, given the raw audio samples, our signal processing algorithm will be able to output the position in AOA and distance. If there are 3 targets, we will see 3 clear peaks in this AOA and distance profile. But things can get more complicated in real environment. For example, under low SNR, the ground truth location indicated by the cross sign is not at the center of the peak. When we have multipass, we may have multiple peaks, and the ground truth location may not be at the highest peak. Moreover, when there's a fast movement, the ground truth position can move outside the peak due to Doppler shift. In order to accommodate all these complexities, we developed, we combine signal processing with machine learning. We use the signal processing to produce this 2D music profile, and then feed that to recurrent neural network to explore this temporal relationship between the position over time. And then we output the target position. In more detail, basically we feed this AOA and distance 2D profile to our recurrent neural network to output the final distance and the angle of arrival. And zooming to our recurrent neural network, each stage, it takes a 2D music profile, and then we use a pooling layer to reduce the input size, and use the first hidden layer to extract features, and use the second hidden layer to combine feature with the previous context to output the distance, AOA, and context information. We are interested in learning what information is being learned in the context. So we perform correlation between the context information with distance, AOA, radial velocity, tangential velocity, radial acceleration, and tangential acceleration. We see high correlation in the distance, AOA, and the radial velocity, which indicates our RNN is learning something meaningful. And this figure shows the performance at different locations. We train our neural network using the data collected from the lab, and then we tested in both lab, conference, cubicle, corridor, and we see the performance is similar. It shows it's robust to different environments. Part of the reason that it is robust is we are not directly feed the raw sample to the neural network. By using our signal processing method, we can significantly remove the background interference and the environment artifact, which make it easier for the RNN to learn the temporal relationship. And this is our demo. In this demo, the two black are the speaker and the four red dots are the microphone array. And the user is 3 meters away from the smart speaker. And the smart speaker is generating inaudible sound, and we receive the reflection from the user's hand, and we let the user draw different geometry shape, and our program can real time trace the shape drawn by the user. It's not a perfect rectangle because the user's trajectory is not exactly following the real rectangle, but you can see that the trace trajectory is very close to our sensed trajectory. And we also directly quantify the tracking error using the depth sensor and show that the tracking error is within centimeter. So far, we have seen several signal processing algorithms for both device-based and device-free tracking. And we also further combine signal processing with machine learning. Our next question is it possible to directly use machine learning to learn this range purely based on data? That is, can we just directly feed the audio sample to the machine learning algorithm to get the distance? Why is that interesting? Well, scientifically, it will be interesting to see, can a pure data-driven approach outperform a signal processing algorithm designed by experts? Practically, it will also be interesting to see if we can get an algorithm that has a higher accuracy, then it will also inform the design of signal processing algorithms. How to enable data-driven approach? The main question is how can we get high quality data? One way to get a high quality data is by performing measurements at different locations using different hardware. But this is labor intensive and time consuming. So instead, we developed a realistic simulation. We use the realistic simulation to generate training data and test it on the measurement from the real testbed. And in our simulation, we first try to just simulate how the signal propagates over a single path, and we vary the distance and the amplitude of the paths, attenuation factor. And then we feed that to the machine learning algorithm to train, and then tested on the data using collected from 10 different phones. And we see that we can achieve 1.9 centimeter median error. So this is promising, but certainly not enough because signal processing algorithm achieve lower error. Can we improve on that? Well, we know that in the real case, we will experience white noise. So we add white noise to our simulation and to our training data, and we vary the degree of noise. And by adding enough diverse noise, we see that the testing performance improve. The testing error now becomes 1.1 centimeter. We further consider that the signal may propagate through multiple paths. We model this multi-paths. We vary the number of paths and the length of the paths. And after adding enough diversity of the multi-paths, we see another big drop in the testing error. Now it becomes 0.58 centimeter, which is already better than the FMCW-based approach. We further realized that in the real setup, even with self-interference cancellation, there's still residual self-interference. We model the impact of residual self-interference in our training data and see another improvement in the testing error. Finally, we noticed that the speaker and microphone has uneven frequency response in this inaudible frequency because they are not optimized for such high frequency. And by adding diverse frequency response pattern in our training data, we see further improvement in the testing error. Now it becomes 0.42 centimeter, which is much better than the existing FMCW-based approach, which is around 1 centimeter error. And this is a comparison between various algorithms. The neural network-based approach is in purple. As we can see, when SNR is high, then all the algorithms perform very well. But interestingly, as the SNR degrades, we see a much bigger gap between the signal processing algorithm versus deep neural network. So this shows that deep neural network has the potential to achieve high robustness, especially under low SNR. So far, we have looked at active sensing. We actively generate a radar signal for sensing purpose. Next, we consider sensing the natural sound from the environment. In particular, we are interested in sensing the user speech. We consider the smart speaker usage scenario because of the popularity of smart speaker. At home, if we are able to use smart speaker to locate the user based on his voice, there are lots of interesting applications we can enable. First of all, if the user is far away, but we can locate them, then we can beamform towards the user and to extend the hearing range for the smart speaker. Moreover, if we know the user's location, when users say turn on the light, we know exactly which light to turn on based on its location. Furthermore, if we know the user's location, we can automatically adjust the temperature near the user, and this can save energy. We can also enable context-aware computing. But how can we localize the user's voice? User's voice is an unknown signal. So traditional method of wireless sensing require, such as channel estimation or distance estimation, requires to know the transmission signal. But interestingly, AOA estimation works without knowledge of the signal pattern. So therefore, this is what we rely on. We estimate the angle of arrival of the user's voice. But in order to locate the 2D position of the user, we need to not only know the AOA from the direct path, but also AOA from the reflected path, so that we can perform intersection. But we notice that in this case, we have coherent multipath, and locating AOA for coherent multipath is very challenging. Existing algorithms experience low accuracy. Moreover, in order to use reflected paths to locate the user, we need to know where is the reflection. In particular, we need to have an knowledge of indoor environment. One way to do that is use depth sensor or cameras, but they are not only privacy intrusive, but also require additional hardware. Instead, we just want to use the smart speaker for both purposes, to compute the AOA and also estimate indoor environment. Furthermore, we want this to work even without line of sight. So, for example, if a user is in different room, if we can estimate where the reflection is, we can still perform triangulation. To do that, we basically need to know the angle of arrival of more than one path, and then the environmental information, and then perform intersection. And this concept works in both line of sight and non-line of sight scenario. Now, it even works without line of sight, because the audio signal especially audible signal can get reflected and go through different rooms. So we developed a system that consists of the following three components. First, we perform AOA estimation, and then we perform room contour estimation, and then we use the retracing to localize the user. Our AOA estimation is built on top of music, but it goes beyond music by improving its ability to estimate the AOA for coherent paths. And this is the performance result. As we can see, compared with Bollock, we can achieve much lower AOA error. Moreover, we can compute much faster within a few seconds. Finally, let's take a look at a few applications we built. The first application is Follow Me Drones. We developed a smartphone app that consists of two components. First, we mount a 2-minute speaker on the drone to emit inaudible sound. It is essentially FMCW chirp in inaudible frequency. And then our microphone will receive the signal and then perform tracking. We then feed the drone's position to the model predictive controller to estimate the exact command to deliver to the drone so that the drone can precisely follow the user to maintain the specified angle and the distance. This is challenging in terms of both the tracking and the control. For the tracking, because the drone can move around furniture, so there's a severe multipass interference. To improve the resilience against multipass, we apply music to FMCW and also compensate speaker distortion in order for music to work well. Furthermore, drone itself will generate propeller noise. So we remove false peak in the spectrum caused by the propeller noise and also apply common filter. To further improve efficiency, we developed subsampling-based approach. We also need to control the drone so that it can follow the user precisely. To do that, we first measure the current distance between the drone and the user. Then we predict the user movement based on the Doppler shift between the drone and the user. Finally, we model the relationship between the drone input and the displacement in order to determine the next input to the drone so that the drone can move at the desirable displacement. And this is our final demo.
We implement the system on Android phones and AR drones and evaluate it in our department building. It follows the user well for all common walking patterns, such as going along a straight line, or a curved path, or making a turn. The system is robust to multipath and works well near furniture or close to a wall. The mobile can be put into a bag or pocket. Audio signals are able to pass through it.
Next, I briefly introduce acoustic imaging on mobile. Why do we want to use acoustic on the mobile? Well, because the speaker and microphone are popular, and compared with camera-based imaging, acoustic can penetrate certain materials, so we can see underneath, for example, underneath clothes to see whether there's any weapon. And it is a software-based approach, so we implement a smartphone app for imaging. Unlike ultrasound imaging, where ultrasound has lots of bandwidth and also has a large transceiver array, on the mobile, doing acoustic imaging is much more challenging because we only have 1 or 2 speaker and microphone, and we only have 3 or up to 6 kilohertz bandwidth. In comparison, the ultrasound has tens of megahertz bandwidth to work with. So to address this issue, to enable acoustic imaging, there are several challenges we need to address: strong self-interference, limited speaker and microphone, and limited bandwidth. So our idea is to use synthetic aperture radar, SAR. At a high level, a point in a physical location, we basically hold a phone and move across the target. And then during the movement, we continuously record the received signal refracted from the target. So S denotes the received signal at a different position of the phone, and K denotes the sample index at a given position. Through data formatting and 2D FFT, we can convert a point in the physical space to a point in the frequency space. And this mapping is one-to-one and also linear. Therefore, by analyzing the shape in the frequency domain, we can recover the shape in the physical domain to achieve imaging. Directly applying SAR to our context does not work because of the following reasons. First of all, there's a strong self and background interference. Secondly, the hand is not going to exactly follow the desired trajectory. There's a noticeable deviation from the desired trajectory due to hand jitter. While there has been some algorithm developed to handle hand jitter, but they assume narrowband signal, point refractor, no quantization error. Therefore, we need to develop a new way of handling hand jitter by addressing these issues. Furthermore, speaker and microphone introduce distortion, which can significantly degrade the image quality. To address the above issues, we developed several modules and combine them with SAR. First, we have interference cancellation. Next, we developed a mobile MPGA to handle narrowband signals and quantization error and also surface reflectors. Furthermore, we developed a compressive sensing-based approach to focus and denoise to address the distortion due to uneven frequency response from the speaker and the microphone. And this is our demo. We let the user hold the phone and move slowly around a straight line. And the phone will continuously record the signal refracted by the target. In this example, our target is underneath the plastic bag because the audio signal penetrates through the plastic bag, so we can see through what's underneath. And this is another trial of the target underneath the bag. Again, we can image the target. To summarize, we show that acoustic-based tracking has some unique advantages due to wider availability and also high accuracy. Of course, in the end, the application dictates the design of tracking algorithms. We also have done some outreach by doing demos at CES, South by Southwest, and also have significant news coverage. In addition to working on acoustic sensing, we have also worked on RFID-based temperature sensing. The idea there is that temperature changes the impedance of the tag, which in turn change the reflected signal. Therefore, by analyzing the reflected signal, we can estimate the temperature. By doing this, we enable battery-free temperature sensor. And this removes the battery replacement in the traditional temperature sensor. In addition, we also enable rotation sensing in RFID. Lots of work consider translation movement, but rotation movement is important, especially in sports analytics. So in this work, we developed an approach that can estimate general movement due to either rotation or translation or combination. And our central idea is we leverage this linear polarization of the FID antenna, and by exploiting this uneven polarization in different directions, we can estimate the rotation, both the speed and the rotation axis, as well as translation moment. Furthermore, we also consider sensing in the 5G context. There, we are interested in estimating the channel. In particular, we are interested in estimating the channel for neighboring base station and also estimating the channel in the future for the same base station. In both cases, we show that we can leverage the delayed Doppler representation of the channel to enable channel estimation for neighboring base station and for future channel prediction. And the high-level idea there is that by leveraging the delayed Doppler channel representation, we can estimate the target movement. And the movement information is more predictable due to inertia than the wireless channel itself, because wireless channel has multipass. Even a slight change in the position can completely change the channel, whereas the movement doesn't have this problem. Moreover, by leveraging movement, we can perform crossband estimation because the movement is invariant across frequencies. And we believe that this delayed Doppler channel representation can also benefit other sensing applications like motion tracking, wireless sensing, and geometric modeling. So thank you everyone for your attention, and I'd be happy to take questions.
Thank you. Thank you very much, Dr. Chiu, for the very exciting presentation. Any question from the audience? We have about 10 minutes, or actually 8 minutes.
Yeah, could I ask a question? This is Anish.
Oh,
Lily, I wanted to echo what Mi said. This was a wonderful talk, a great piece of engineering and very nice consideration of, many elements. If I understood the passive sensing part of your talk correctly, you were very nicely showing where a learning-based approach combined with some carefully engineered features could compete quite well. And I guess I had a couple of things I wanted to ask you. One was, when you think about making this generalize across different clutter environments, how did you go about that? And did you also consider how small could the learning-based components be made so that they could be engineered on different types of devices?
You're referring to the neural DNN-based sensing?
Yes.
Oh, okay. Yeah. So for DNN-based sensing, our test data come from 11 different smartphones, and we also collect the measurement using different users' hand at different environment in the lab, in the corridor, and at the cubicle. So the performance is pretty good, and as you can see, it's significantly better than the existing FMCW or finger IO LLAP. And in fact, we also learned a few insights why this machine learning is doing better than the traditional algorithms. So in the traditional algorithm, we only leverage the received signal during the transmission period. But it turns out the machine learning algorithm also leverage the silence period. So that's an interesting insight that we could potentially incorporate. So maybe our future signal processing algorithm can also leverage that part. Another reason that it is performing better is because it has an interest. So in FMCW, we are just doing the mixing between the received signal and the receive signal and the transmission signal once. But we noticed that DNN somehow is doing this kind of sliding window based approach. And this is likely to help in the uneven frequency response case, because during the mixing, if we only do it once at different frequency point, if the speaker and microphone has a different amplitude, this can introduce distortion. But doing in the sliding window manner, it is likely to be more robust. So yeah, there are a few things. It seems that DNN is doing better, and in retrospect, it makes sense. And we are very interested in incorporating this kind of feedback to the traditional algorithm as well. Does that answer your question?
Yeah, and the second one about, did you look at different forms of scaling this DNN? Did you look at, techniques by which this could preserve its accuracy and robustness without, while shrinking it in some sense? I'm curious. I mean, DNNs can be quite small, but I was curious how small you could make it.
Oh, that's another interesting question. So, in fact, we tried a traditional CNN using a small kernel. It doesn't work very well, and so we gradually increased the size of the kernel, and it started to work well when the kernel size is close to the FMCW chirp length, which sort of makes sense. But if we just replace, and in fact, the best kernel has a high correlation with our transmission signal, the FMCW signal. But interestingly, if we just replace the kernel with the FMCW, it's not as well. So it turns out we need to have some diversity in the kernel, and it's similar, but it's not identical to the FMCW chirp. So FMCW chirp has, in our case, has around 1,500 samples. So the kernel is relatively larger than the typical CNN kernel. But this is required because our transmission signal is at that duration, and we found that works the best. But the number of layers is very small. We if I remember correctly, it's only 4 or 5 layers. Yeah.
Great, thank you.
Thank you.
I think I wanted to briefly comment on the first question related to the DNN, why is outperforming. I think another factor I noticed that is probably because of the simulation environment, the work being developed, because I think in a simulation, you basically try to simulate all the possible scenarios that can come up with kind of simulated data, under different scenarios, like different indirect passes, right? So you can use that data to train the model such that the model learns or being robustic to all those possible noisy factors, for example, multipass, white noises, something like that. I think that might be another factor why the EM-based method is outperforming the conventional signal processing approaches.
Yeah, signal processing is designed for the ideal case, and the DNN. Yeah, after seeing diverse enough scenarios from all these major factors, it indeed learns something meaningful, and the final structure could be potentially inform our signal processing method. Yeah.
Okay, thanks so much. Any other question from the audience? I actually have a follow-up question. We see many Wi-Fi based sensing. So where you present primarily on the acoustic sensing. I wanted to have a better understanding how like given that we have so many smart speakers, right, in the home and in the environments. So do you see there's some edge of acoustic sensing over wireless sensing in particular applications?
Yeah, I think the biggest advantage of acoustic sensing is wide availability of devices. It's much easier to deploy. All we need is a smartphone or smart speaker. But Wi-Fi, in order to get good accuracy, we need to have software-defined radio like a system. Because in order to have gigahertz bandwidth, we need this kind of more sophisticated setup. So I think for ease of development, the acoustic sensing will win. In terms of range, Wi-Fi has an edge. It has better penetration through wall and also a larger distance. But this is a double-edged sword because you may not want to see through your neighbor, or your neighbor doesn't want this kind of see-through capability. It can be more privacy intrusive. At least for the device, everything is kind of within a room, so less privacy concern there.
Yeah, I think that makes sense. Yeah, well, I see, like, for example, Google has this product based on, I think, millimeter wave sensing,
Yes.
where they use this tablet format, device that put beside your bed for sleep monitoring, something like that. But I do see there's also opportunity for acoustic sensing for doing the same thing. Just maybe you can what's your opinion on this?
Sorry, my internet got break. Yeah, I'm back.
Oh, no worries. So I think my last question, I think, is basically I do see some products from Google side. They have this millimeter wave sensing device that monitors people's sleep. But I do see there's an opportunity for this acoustic sensing technology to do very similar things.
Yeah, indeed, we are developing that. We also have a version of that already on the phone, and we also have an initial prototype on the smart speaker as well. Yeah, acoustic sensing in that case, we just download an app. You don't need to buy additional millimeter wave device.
Great. Any other question from the audience? If no, we can add here. I think it's kind of late in Beijing time. So we want to thank you again, Dr. Chiu, for taking your time to give us a fantastic presentation today. Thank you so much for taking your time.
Thank you so much. Thank you so much, Professor Zhang and everyone.
So this gonna basically concludes the OSU IoT seminar series for this semester. We're gonna resume this semester, this seminar series next semester. We'll see you everybody next semester then. Thanks again, Dr. Chiu.
Thank you.
Thank you.
Bye.
Bye, everyone.
All right, thank
Bye,
you.
everyone. Thank you.